Hello guys. Hello. Hello. Hello guys. Hello. So in this video we learn Rust programming language. So we learn up to loops. We learn Rust programming language. When we the loop keyword tells us to execute a block of code over and over forever until it explicitly tells it to stop. This is a function or something that runs until you stop through explicitly. You should give it execute until you explicitly enter Control C. You click on Control C, it will stop and come out of it. And the conditional loop with while. It is often useful for a program to evaluate a condition with a loop. When the condition is true, the loop runs. When the condition says true, let's stop the loop. The loop type could be implemented using a combination of loop, if else, and a break. You could try that now in a program. Something however, this pattern is so common that Rust has a built-in construct called a while. Listing use the while program loops 3 times, one each time, and then after the loop it prints another message that exists. And let new constructor while number short and notation for just print it. That's how let's send it. Workaround 3, 2, 1 left. That's it. This is a while loop. There is no parenthesis for the condition in Rust, and basically you keep a condition. You take a mute variable, but just for a variable, immutable variable, you should keep this mute, or else you can remove and you can use the let keyword. Let key. If you oh shit. What happened? Let 3 number equals to 3, number not equals to it will it again checking with this. Oh, only work. Not okay. Next, looping through a collection with for this construct. This is basically a construct. This construct eliminate a lot of nesting that would be necessary if you used loop, if else, and break. It clearly clearer while a condition holds true it runs. Otherwise it exists the looping through a collection with let's see collection looping collection. Okay, let's go. Again we are using by not a for loop that is basically there in any other programming like for variable condition increment iterator plus like but we are using add outlet. We can specify in add outlet. Values of index post incrementing length. There is no length. This length. There is no incrementing. We can use short annotations instead. Okay. Okay, let's not a value push to fix operation. You are learning. You are currently learning steps. Okay. It gives the purpose. But why this line appears down here? Okay, next looping through each element of collection using a while. Using a while, here the code counts up to through the in elements in the array. Let's start at index 0 and then loops until it reaches the final index in the that is where index less than 5 is no longer. Running this code will print every element in the that's all that we got here. All 5 array values appeared in the terminal as expected, even though index will reach value 50. 5 index value 5 at a point. The loop stops executing before trying to fetch sixth value from the array, but this approach is error. We couldn't cause the program to panic if the index length is not. It also slow because the compiler and runtime would to perform condition check on every element on every iteration through the code. As more concise alternative, we can use a for loop here, a for loop, and execute some code for each item in the collection. A for loop looks like the code in this table. This is for loop. We declare for let element in I dot item print element. When we run the code, we'll see same output as in listing 3. More importantly, we have now increased the safety of the code and eliminated the chance of further might result from getting beyond the end of array or not keeping far enough or missing some items. For example, in the code, if you remove an item from the array but forget to update the condition to file index for the code panic. Using the for loop, you won't need to remember to change any other. If you change the number of values in the array, the safety and consciousness of for loop makes them most widely used loop construct in Rust, even in situations in which you want to run some code a certain number of times, as in the compound example that used the while loop in listing 3.3. Most Rustaceans would use a for loop. The way to do that would be use a range, which is type provided by the standard library that generate all numbers in sequence starting from 1, 2 and ending before another number. Here for the compound program, like using a for loop and another method, we have a object top about to reverse the range. For numbering 1 to 4, dot reverse print number. What we could show. I do print 432. Print one. Forest exclusive doesn't add to the okay. That's it. Summary, you made it. That was sizable chapter. You learned about variables, scalar and component types, functions, comments, expressions and loops. You want to practice with concepts discussed in this chapter. Try to build try, try building the programs to the following. Your temperature between Fahrenheit and Celsius, generate the plus number, print the lyric, your Christmas carol, the 12 days of Christmas, taking advantage of repetition in the song. When you are ready to move, we'll talk about concept interest that doesn't commonly exist in other programming language called ownership. Build understanding ownership. Ownership interest most unique feature and it enables us to make memory safety guarantees without making a garbage collector. Therefore, it is important to understand how ownership works in this chapter. We'll talk about ownership as well as several related features, borrowing, pricing, and trust-based data container. What is ownership? Trust central feature is ownership. Although the feature is straightforward to explain, it has deep implications for the rest of the language. Our programs have to manage the way they use the computer's memory while running. Some languages have garbage collector that constantly looks for no longer used memory as program runs in other languages like Java. The programmers must explicitly allocate and free the memory. It uses a third approach memory. Third approach memory is managed through a system of ownership with a set of rules that the compiler checks at compile. Some of the ownership features slow down your program while it's running because ownership is a new concept for many programmers. It does take some time to get use it too. The good news is that the more experienced you become with the rules of ownership system, the more you will be able to naturally develop code that is safety efficient and efficient. Keep at it. When you understand ownership, you will have a solid foundation for understanding the features that make Rust unique. In this chapter, we'll learn ownership by working through some examples that focus on very common data structures, the stack and the heap. In many programming language, you don't have to think about the stack and the heap very often. But in a system programming language like Rust, whether a value is on stack or heap has more of an effect on what the language behaves and when you have to make certain decisions. Parts of ownership will be described in relation to stack and heap later in this chapter. So here is a brief explanation in preparation. Both stack and heap are part of memory that is available to you code at both to use at runtime. But they are structured in different ways. The stack stores values in order, in the order to get them and remove the values in a position opposite order. This refers to as last in first order. Think of stack of plates. We remove the plate that is on the top of on top, and we remove the plate which is we remove the last plate at last, which is at the bottom. When you add more plates, you put them on the top of the pile. When you need a plate, you take off the top. Adding and removing plate from middle or bottom wouldn't work as well. Adding data is called pushing the stack, and removing the data is called popping off the stack. The stack is fast because of the way it accesses the data. It never has to search for a plate to put new data or place to get data from. Because that is that because that place is always the top. Another property has makes the stack fast is that all the data on the stack must take up a node, a fixed size. Data with a size unknown, a compile time, or a size that might change can stored on the heap instead. The heap is less organized. When you put data on heap, you ask for some amount of space. The operating system finds an empty spot somewhere in the heap that is big enough mark it has been used and return a pointer, which is the address of the location of that location where the data is being allocated in heap memory. This process is called allocating on the heap, sometimes abbreviated as just allocating. Pushing values on the stack is not considered allocating because the pointer is known fixed size. You can store the pointer on the stack, but when you want actual data, you have to follow the pointer. Uh, think of big seated at the restaurant. When you enter, you state the number of people in the group and the staff. An empty table that fit everyone and leave you there. If someone in your group comes late, they ask, they can ask where you have been seated to find you. Accessing data in heap is slower than accessing data on the stack because you have to follow a pointer to get there. Contemporary processors are faster if they jump around less in memory continuing the analog. Consider a server at restaurant taking order from many tables. It's most efficient to get all the order at the one table before moving to the next table. Taking an order from one table A, then order from table B, then order from table A again, and then from B would be much slower. By, by, by the same token, a processor can do its job better if it works on the data that closer to the data, as it is on the stack rather than far away as it can be on the heap. Allocating a large amount of space on the heap can also take time. When you when your when your code calls a function, the value passed to the function including potentially pointer to the data on the heap, and that function's local variables get pushed on the stack. When the function is over, those values get popped off. Keeping track of what part of the code are using what data on the heap, minimizing the amount of duplicates data on the heap, cleaning up unused data on the heap so you don't run out of the space. All problems that ownership has. Once you understand ownership, you will need to think about the stack and heap every effort. But knowing that managing heap data is why ownership exists. Can explain why it works the way it does. Ownership rules. First, let's take a look at ownership rules. Keep these rules in mind as work through the examples that illustrate them. Each value in Rust has variable that called its owner. That's called its owner. There can be one owner at a time. When the owner goes out of the scope, the value will be dropped. Variable scope. Let's talk variable scope. We have walked through an example of Rust programs already in chapter 2. Now that we are past basic syntax, we won't include all main function code. So if you are following along, you have to put the following examples inside main function manual. As a result, our examples will be a bit more concise, letting you focus on details rather than boilerplate code. And the first example of ownership, we'll look at the scope of some variables. Scope is a range within a program. If let's declare a variable this is scope, this variable and scope within its function. Here you can't access that username variable because username variable equals. This variable is defined in this block of code where this block is within this after the variable name got dropped off. That's all. Okay. So let's say the variable refer to string. This is that's all. A string literal where the value of the string is outputted into a text of output. Variable is valid from the point at which it declared until the end of the current scope based on for. Do stuff with s up to this text. After being used, it won't be retrieve the value of this variable. We can do anything with this. When s comes into scope, it is valid, it remains valid until it goes out of the scope. At this point, the relation between scope and the variable that are valid is similar to that other programming languages. Now we'll build on the top of this understanding by introducing the string type. Two string types. String types. The string type. To illustrate the rules of ownership, we need a data type that is more complex than the one we covered in data types. On page 36, the types covered previously are stored on stack and popped off the stack when their scope is over. But we want to look at data that is stored on heap and explore how Rust knows when to clean up the data. We'll use string as an example here and concentrate on part of string that relates to the ownership. These aspects also apply to other complex data types provided by standard library and that you create. We'll discuss strings in more depth in chapter 8. We have already seen string literals where a string value is outputted into our program. The string literals are convenient, but they aren't suitable for every situation in which we may want to use text. One reason is that they are immutable. Another is that not every string value can be known when we write our code. For example, If we want to take username input and store it, for this situation, Rust has a second string type on string. This is a type. This type is allocated on heap, and such is able to store amount of text that is unknown to us at compile time. We can create a string from a string literal using the function using the from function like this. Okay. Is equals to this being stored equal. Hello being stored on heap. The double semicolon is an operator that allows us to namespace this particularly from function underscore string type rather than using some sort of names like strings underscore from. We'll discuss this syntax more in method syntax on page 20. Okay. When you want to talk about naming space with modules in module definition of page 111, this kind of strings can be muted. Okay. Now we can add s to module. We can add data group, push here. Appends a literal to a string, but in empty space, I think so. Okay. Whatever expected expression, natural expression. Okay, this is what it is. Mute. I will initialize this with mute. Initializing the variable mute. And I should print it. Hello. Oh. Okay, this is a string. Whenever the comma is being added to the end of this variable. Okay. Yeah, sure. Println. So, what's the difference here? Why can a string can be muted, but literals can't? The difference is how these two deals with memory. Okay, literals are this string literals. Let A struct with similar name exists. I can't keep it a string. Method not found. Interest string literals are immutable. Reference to string data. If you want to append it, you should use string. Okay, these are immutable by default. Reference to string data is stored in binary. You can't push a string literal directly because they are immutable. But they are of type asterisk, not string. String dot push here. We are converting string literals to string and again pushing string to this string. Yeah, that's this missing to Okay, now let's understand. Let's start learning memory allocation. These string literals are immutable by default. Okay. Memory allocation. In case of string literals, we know the content at compile time. So the text is hard-coded directly into the final executable. This is why string literals are fast and efficient. But these properties only comes from the string literal. From the string literals immutability. Unfortunately, we can't put a block of memory into a binary or piece of text whose size is unknown at compile time and whose size may change while running the program. With this string type, in order to support mutability, global piece of text, we need to allocate an amount of memory in the heap on a compile time. To hold the content, this means the memory must be requested from the operating system at runtime. We need a way of returning this memory to the operating system when we are done with our string. That first part is done by using us. When we call string colon from, it implementation requests from memory it needs. This is pretty much universal in programming language. However, the second part is different. In languages with garbage collector (GC) that keeps track and clean up memory that isn't being used anymore, and we don't need to think about it. Without a GC, it's our responsibility to identify when memory is no longer being used and call code to explicitly run it, just as we did to request it. Doing this correctly has historically been difficult programming. If we forgot, we'll waste memory. If we do it too early, we have invalid variables. Okay. If we do it twice, that's a bug. We have to pair exactly one allocate with exactly one. First it takes a different the memory is automatically returned once the variable that owns it go out of the scope. Here is the version of our scope example from the listing. This is valid for this point to stuff within this. Okay, we know there is natural point at which we can return memory. Our string needs the operating system. When eggs go out of the scope, when a variable go out of the scope, first calls a special function for us. This function is called drop, and it is where the author of string can put the code to run the memory. First calls stop automatically at the closing bracket. In C++, this pattern of deallocating resources at the end of the item's lifetime is sometimes called resource acquisition. Is initialization. The drop function in Rust will be familiar to you if you used RAII patterns. Okay. This pattern has profound impact on the way Rust code is written. It may seem simple right now, but the behavior of code can be unexpected in more complicated situations when you want to have multiple variables. Use the data to be allocated on the heap. Let's explore some of these situations now. ways the variables and data interact, move, multiple variables can interact with same data in different ways. Let's look example. Let x equals to 5, y equals to 5, assigning the integer values to variable x. We can probably guess what this is doing. When the value 5 to x and then make a copy of y equals to x and make a copy of value in and bind it to y. We know we now have two variables x and y and both values 5. This is indeed what's happening because integers are similar values with non-fixed size, and these two high values are pushed onto the stack. Now let's look at the string version. Let this one is equals to is equals to s1. Basically, this is a pointer. We are getting pointer of hello. Think as hello is allocated in random location, and we are getting pointer of hello from that location, and we are assigning s1 a pointer. If we print s1, just print then it should print. It is printing hello. This looks very similar to the previous code, so we might assume that it would be the same. This is the second line would make your value s1 and bind, but this is not quite what happened. Take a look at figure 4.4. What is happening to string under the cover? The string is made up with what I shown below. A pointer to the memory that holds the content of string, length, and capacity. The group of data is stored on this group of data is stored on stack. On the right is the memory that holds the content. Value 5 length capacity. The length is how much memory in the content of the string is currently used. Capacity is the total amount of memory in bytes. The length is how much memory in bytes the content of string is currently using. The capacity is the total amount of memory in bytes. That is the string that has received from the operating system. The difference between the length and the capacity matters. When we assess the difference between length and capacity matters, but not in this context. So for now, it's fine to ignore the capacity. When we assign S1 to S2, the string data string data is occupied, meaning we copy the pointer, the length, and the capacity that are on the stack. We don't copy the data on the heap. The pointer that the pointer refers. In other words, the data represents in memory look like. What memory would look like if first instead copy the heap as well. If first did these operations S2 is equals to S1 could be very expensive in terms of time performance if the data on the heap are very large. Earlier we said that when a variable goes out of the scope, Rust automatically calls the drop function and cleans up the heap memory for the variable. But 4.2 shows both pointing to same. Rust automatically calls the drop function claims. Shows both data pointer pointing to same location. This is a problem when S1 and S2 goes out of both try to free the same memory. This is known as double free error, and this is one of the memory safety bug we mentioned previously. The memory bias can lead to memory corruption, which make potentially lead security variables. To ensure memory safety, there's one more detail. What happens if in this situation, instead of trying to copy the allocated memory, just consider this one will no longer be valid, and therefore Rust doesn't need. Okay, we can't print. Okay, S1 error. Yeah. Value borrowed here after move. Note that move occurs because S1 has type string which doesn't implement the copy. Value moved here borrowed after move. This error originates in the macro grades, uh, which comes from the expression of macro println. We can clone it. The ownership has moved. Yes. Ownership of S1 is moved to S2. So S1 has been destroyed. The ownership of S1 is moved to S2. If the ownership is moved, your power if your powers has given to someone, then you don't have any powers. That's being used here. That's all. Okay. Instead of giving powers, total powers of here, you can just give them like a little bit powers. So only what they can do. Clone. This is what it can do. It can clone and you can keep our ownership safe. To ensure memory safety, there's one more detail to explain what happened in this situation in Rust. Instead of trying to copy the allocated memory, Rust consider S1 no longer to be valid, and therefore Rust doesn't need to be anything. When S1 goes out of the scope, check out what happened when you try to use S1 after S2 is created. It won't work. You will get an error like Rust prevent you from using the invalid reference value used after move. Move occur because S1 has type std string which does this implemented track. If you have here the term shallow copy, deep copy while working with other programming languages, the concept of copying the pointer length capacity without copying the data probably sounds like making a shallow copy. This is what called shallow copy. This is clone. This is copying, shallow copy. But because Rust also invalidates the first variable, instead of being called a shallow copy, it's known a move as a move. It's known as a move. This is what we call move. In this example, we could say that S1 was moved into S2. So what actually happened is that 4.1 solves a problem. S1 is being moved to S2. Initially, S1 points to this index. After we are again pointing S2 to that. So the pointer that solves our problem with only S2 valid. When it goes out, it along will free the memory and we are done. In addition, there's a design choice that implemented by this. Rust will never automatically create deep copies of your data. Therefore, any automatic copying can assume it to be inexpensive in terms of runtime performance. Ways that variables and data interact. Cloning. If we do want to deeply copy the heap data of string, not just the stack, we can use a common method called clone. We can clone without losing ownership of a variable. We'll discuss method syntax in chapter 5, but because methods are common feature in many programming languages, we probably see them before. There is an example of clone. We can easily clone a string by dot clone method. This works just fine and explicitly produce the behavior showing where the heap data does get copied. When you see a call to clone, you know that some arbitrary code is being executed and that code may be expensive. It's a visual indicator that something different is going on. Stack only data. So I'm going to end this session here. Thank you guys.